Okay guys, let's talk about the elimination mechanism today. Most simply, a base is going to come along, it's going to pluck off what we're going to call a beta hydrogen, and it will create a double bond, kicking off a leaving group as a result. In this video, we will quickly analyze the E2 mechanism. In this particular mechanism, we need a strong base. Now remember, a base likes to steal hydrogens, and what we're calling strong is merely having a formal charge of -1. This entire process is concerted, so this proton transfer, this formation of the double bond, and this loss of leaving group, it all happens at the same time. But I'm going to break it down in a few different steps to make it a little simpler to understand. So here is our strong base, in this case, this hydroxy ion. The alpha carbon is the one that contains the leaving group. It will almost always be a halogen. And then your beta carbon is any carbon directly touching the alpha carbon. So here comes our base. It's going to pluck off a beta hydrogen. This lone pair is merely the covalent bond between carbon 1 and the hydrogen that the hydroxy ion just plucked off. It is going to be attracted towards the partial positive charge on the alpha carbon. And when it does that, it's going to form this double bond. Well, then that's too many bonds coming out of carbon 2. So we got to kick someone off because we're in violation of the octet rule, specifically the leaving group in this case. The shortcut is merely to identify your alpha carbon, which is the carbon containing your leaving group, and then your beta carbons. And unless you're asked to draw the mechanism out, which I found is pretty rare on tests, just know that the only place the double bond can form is between the beta carbons and the alpha carbon, provided that the leaving group and the beta hydrogens are anti-paraplanar. These types of problems should take you less than 10 seconds on test day. Let's try a few examples so we can see what's going on. So again, alpha, beta, beta. The only place the double bond can form is between the beta and alpha. So I can quickly look at this problem and be like, oh, a double bond will form between 3 and 2, between 2 and 1. And your more stable alkene is what we call our major product. This is Zaitsev product. And your least substituted alkene is what we're going to call our Hoffman product or our minor product. The Zaitsev product is always going to be your major product unless a big bulky base is used, such as tert butoxide. So here we're dealing with a primary substrate. We're calling it primary because the alpha carbon is directly connected to just one other carbon. So remember, our goal is 10 seconds or less on these types of problems. So here's our strong base. Alpha carbon, beta. The only place double bonds can form is between the beta and the alpha. So we redraw our carbon skeleton and we're going ahead and tack on a double bond between 2 and 1, and we're done. Secondary substrate. We're calling secondary because alpha carbon directly connected to 2 other carbons. So alpha, beta, beta. The only place a double bond can form is between beta and alpha. So I'm expecting a double bond to form between 3 and 2, 2 and 1. So 3 and 2, 2 and 1. This is our Zaitsev because that's the more substituted alkene. This is the Hoffman because that's our minor, least substituted alkene. And we're done. Lastly, let's check out a tertiary substrate. Tertiary because here's the alpha. It is directly connected to 1, 2, 3 other carbons. So alpha, beta, beta, beta. So I'm expecting a double bond to form between 1 and 2, 2 and A, 2 and 3. So I've redrawn the carbon skeletons. Let's draw double bonds in all the places we just mentioned. 1 and 2, 2 and A, 2 and 3. So what looks like 3 products is actually just going to be 2. And we can confirm that if we try to name this molecule. So if we try to name this molecule, we have a 4-carbon chain. So butane. Meth, eth, prop, bute is 4 carbons. We have an alkene between carbons 1 and 2, so this is butene. So this is and a methyl group coming off of carbon 2, so 2-methyl-butene, okay? Now, this looks different, but it's not, because if I try to name it, so the carbon number would be a little different here. This would be carbon 1. This would be carbon 2, because you want the alkene to occupy the lowest carbon number possible. 3, 4. So this is still also 2-methyl, because there's a methyl group coming off of carbon 2, 2-methyl-butene. So because these look a little different, but they have the same name, they're the same answer, they're the same product. So I actually have 2 answers and not 3 here. This is our most substituted alkene, so this is our Zaitsev product. This is our least substituted alkene. This is going to be our Hoffman product. Again, shoot for 10 seconds or less on these types of problems. If you found this video helpful, please like, comment, and subscribe to any of the videos that you see on our YouTube page. Share it with your classmates, and go to our website, www.orgogoat.com, to see the full-length version of this video as well as other concepts explained in depth. And if there's a concept you'd like to see that we don't currently have, shoot me an email, orgogoat@yahoo.com. And also, if you're interested in private tutoring, we can help you out there as well.